Okay, again, in the x equals 4 plane you have z equals the square root of y plus 4. In the y equals 9 plane you have z equals x plus 3. This figure is similar to the one I did before, where this is your point 490, and this is your point 497. Previously, we sketched short line segments that were equal to or approximately equal to segments of tangent lines. They were approximate segments of tangent lines. Now we're going to draw these curves as appropriate. Well, this curve is in the x equals 4 plane. It starts up here at z equals, well, it's a function, z equals f of 4y. When y equals 9, maybe at this point, then where are we? We're at the point 497. And this curve is going to look like maybe this. We'll be at this point on the curve and then subsequent points. The curve in the y equals 9 plane, the y equals 9 plane being the one that's cut at y equals 9, that would be the plane of this rectangle, is going to be a straight line. So we could draw that. Again, these are two corners of a room, back wall, side wall. Straight line along the side wall, some curvature along the back wall. We want to get the exact equation of the tangent plane, because the equation we got previously was based on evaluating the function at two nearby points, at 490 and at two nearby points, 4.190 and 49.20. How are we going to get the exact value? Well, let's think about it. Okay, in the yz plane, we have again the function z equals square root of y plus 2. The derivative of that function is 1 over 2 square root of y. So at any given point, we plug in the y value and we get the slope of the curve, which means that the slope of the curve at the point where the x equals 4 plane and the y equals 9 plane meet, which would be this point here, the slope in this direction is going to be 1 over 2 times the square root of the y value. The y value is 9. So the slope is going to be 1 over 2 square root of 9, which is approximately 0.167. So here's the kind of the picture. We have the y-axis here. We use the points where y is 9 and 9.2 as a basis for our approximate line. If we want the slope of the actual tangent line, though, we don't do it from the y equals 9 point of the graph to the y equals 9.2 point. That would be a chord of the graph. We do it instantaneously at the point, and that's where we take the derivative. So we get the derivative at this point. It gives us the exact slope here, and using that exact slope we can get a vector, same way we did using our approximate slope. So at y equals 9, z equals 4 plus square root of 9 equals 7. At y equals 9.2 we got this. That gave us our, I'm in the middle of a sentence and I hadn't looked forward, I apologize. That gives us a very good approximation, okay? If we use those values, square root of 9.2 is about 3.033, so that our rise over our run, the slope between the 2 points on the graph, and it's 9.2, not 9.02. The slope between these 2 points on the graph is going to be very close to 0.167. Although if we evaluate the square root of 9.2 to more significant figures, we actually end up with 0.01657. If we use the exact slope, we get exactly 0.1666 repeating, which differs from this out here in this fourth significant figure. We're off by almost 1 part in 1,000 if we use this value as opposed to this value. Okay, so that by using the values at these points, we have limited accuracy. Okay, we have pretty good accuracy, but there are limits, and we might want to use the exact value. Okay, the big point is, to get the exact value though, we just use the exact slope. We don't use an approximated slope.